Dawn breaks over the edge of the kelp forest, the ocean surface shimmering with the pink and gold tones of a rising sun. A hush settles on the waves, broken only by the cry of distant seabirds and the soft slap of swells against a whale's immense, lifeless body. The carcass floats in gentle rhythm with the tide, its skin scarred with tooth marks, its ribs exposed like the beams of a broken cathedral. And there, breaching the stillness, is the unmistakable silhouette, a great white shark. Not in pursuit of a terrified seal, not erupting from the deep in a cinematic strike, but circling, patient, its movements deliberate as it carves strips of flesh from the whale. This is the reality that the posters, the films, and the headlines rarely show. The most feared predator in the ocean is, in this moment, not the relentless man-eater of lore, but a scavenger. The myth of the shark as a single-minded killer cracks open in one shot. For decades, the great white has been cast as the apex hunter of nightmares, an animal driven by bloodlust, leaping from the sea to drag seals into the deep. While this image is not entirely false, it is deeply incomplete. Scientists have spent years documenting white shark diets, and what emerges is a story that is more complex, more opportunistic, and more ecologically subtle than most imagine. The white shark is a hunter, yes, but also a forager of the ocean's leftovers, relying heavily on scavenging events like drifting whale carcasses. These floating banquets are caloric jackpots. A single bite of whale blubber delivers such energy that it dwarfs a day's worth of chasing smaller prey. Instead of exhausting themselves in endless pursuit, sharks often wait for the ocean to deliver its own feast. Carcasses are not accidents in their world. They are events, shaping movement, migration, and even the concentration of individuals in coastal waters. And when the myth of constant predation fades, a more accurate image surfaces: the shark as a strategist of efficiency. This balance between hunting and scavenging is written into their physiology. White sharks are endothermic fish, capable of regulating body temperatures above that of the surrounding water, thanks to specialized networks of blood vessels known as rete mirabile. This adaptation allows them to strike with bursts of speed and sustain long patrols through colder seas. But such a system comes at a cost. It demands immense fuel. Hunting fast, slippery seals is one way to pay the metabolic bill, but so is stripping fat from the buoyant corpse of a whale. A whale carcass provides an almost absurd return on investment. Each thick layer of blubber is dense with lipids, the highest energy currency in the animal world. Studies suggest a single adult whale carcass could feed hundreds of sharks over weeks, supporting not only individuals, but entire predator communities. What the documentaries show as random chance encounters with humans at surf breaks are, in many ways, side effects of an animal designed to maximize caloric intake wherever the opportunity appears. And yet the myth of the attacker persists, fed by a series of mistaken encounters. The reason lies in optics, not the metaphorical kind, but the literal physics of light in water. Beneath the surface, light bends and fractures. A surfer lying belly down on a board, arms paddling, presents a silhouette eerily similar to that of a seal, especially when backlit by the sun. Through Snell's window, the circular portal of refracted sky visible from below, a shark sees an object framed in glare and distortion. Evolution has taught the shark that silhouettes framed against brightness often mean prey. Pinnipeds returning to rookeries, penguins clustered after a dive, or seabirds resting precariously on the surface. A single investigatory bite is often enough to resolve the error, but for the human on the board, that moment becomes legend, repeated across media as evidence of a killer's intent. In reality, it is a failure of optics, not a strategy of predation. Most sharks release humans almost instantly. Lean, bony flesh is not worth the expenditure compared to blubber-rich seals or whales. The shark's reliance on very particular hunting windows also reveals how tightly bound they are to ecological rhythms. Along South Africa's False Bay, for example, sharks rise at dawn and dusk to patrol seal haulouts, using the low light to mask their approach. In these precise moments, they surge from below, striking seals with explosive ambushes that rely on surprise more than endurance. But outside these windows, the same waters can feel empty of danger. The white is not an indiscriminate hunter, it is a specialist bound to cycles of light, tide, and prey behavior. The myth of constant threat does a disservice not only to the animal, but to our understanding of how ecosystems balance predator and prey. When orcas began appearing more frequently in these regions, killing white sharks and consuming only their livers with surgical precision, the balance shifted dramatically. Whites fled long-used territories, leaving seal and penguin colonies to grow unchecked. The ripple effect of orca pressure shows how predators regulate each other and how removing one from the system, whether by human culling or inter-predator displacement, reverberates far beyond a single species. This raises an uncomfortable truth. Human attempts to manage the shark problem often magnify the very dangers they claim to address. Drum lines and culling programs, deployed along coasts in response to rare shark bites, aim to reduce shark numbers near beaches. But these measures are blunt instruments. They kill indiscriminately, catching turtles, rays, dolphins, and non-threatening shark species in their hooks and nets. In some cases, they even disrupt the very dynamics that stabilize shark behavior, leading to shifts in prey populations and unintended ecological consequences. Alternative approaches, such as aerial drones that spot sharks in real time, smart drumlines that tag and relocate rather than kill, or beach protocols based on seasonal shark movements, show promise. They align with the truth of shark ecology. These animals are not patrolling beaches in constant hunger, but moving through specific zones and times dictated by physics, energy, and opportunity. Protecting both humans and sharks requires acknowledging this precision rather than clinging to myths. There is also the paradox of perception. By branding the shark as a monster, policies often escalate into destruction. Yet by seeing the shark as it truly is, a scavenger, a hunter, a critical regulator of marine systems, we find reasons to conserve rather than eliminate. Sharks prevent pinniped colonies from overwhelming fish stocks. They recycle whale biomass back into the food web, feeding scavengers from hagfish to seabirds. They maintain the health of prey populations by targeting the weak, the injured, and the inattentive. In their absence, marine ecosystems tilt toward imbalance, prey species swell, and fisheries collapse under the weight of unchecked consumers. The killer is, in truth, a steward of equilibrium. And so the whale carcass at dawn tells a different story. The shark circles, lunges, and tears, not with reckless frenzy, but with deliberate efficiency. Each bite releases oils that shimmer in the sunlight, attracting other sharks, smaller fish, and clouds of seabirds. The scene is less massacre and more communal redistribution of resources, a reminder that death fuels life in the ocean. From a single carcass, nutrients will cascade across food webs for months, even years, as bones sink into the deep to become oases for entire new ecosystems. At the center of this process is the great white shark, not as the singular terror of human imagination, but as one participant in an endless cycle of energy. The takeaway is clear. The image of the white shark as a man-eating killer obscures its role as both scavenger and precision predator. Its behavior is guided by light angles, tidal windows, and carcass events rather than by blind hunger. Its distribution is shaped not just by its own choices, but by the presence of orcas and the policies of humans. To understand the great white is to see past the myths, to watch the dawn at the kelp line, where the shark rises not for the thrill of the hunt, but for the pragmatic opportunity of a drifting whale. Behind the legend of the killer lies an animal of calculation, adaptation, and ecological necessity. Inside a rocky crevice, the ocean holds its breath. The water is still, filtered through the slow pulse of a tide, carrying faint flecks of plankton that drift like cosmic dust in a beam of blue light. If the eye adjusts to the shadows, a vision emerges, thousands of tiny pearly ovals strung like moons in delicate garlands. They sway in the faint current, glowing softly against the gloom of the cave. Their guardian hovers close, her skin shifting between muted mottles of grey and cream. She is an octopus mother, her body drawn thin from weeks of fasting. Just beyond the entrance, a crab scuttles across the sand, prey she would have leapt upon with explosive grace only months earlier. Now she does not stir. Hunger claws at her, but her watch is absolute. She will not eat again. The octopus mother is caught in one of the ocean's most haunting biological scripts, a maternal sacrifice dictated not by choice, but by a molecular switch. Deep in her body lies the optic gland, a small structure near the brain that serves as a hormonal command center. Before she lays her eggs, this gland pulses quietly, regulating growth and reproduction. But once the eggs are anchored to the cave wall, something extraordinary happens. The optic gland undergoes a dramatic transformation, releasing a cocktail of chemicals that rewires the mother's behavior completely. Appetite shuts down, hunting ceases. In its place, an obsessive devotion to care emerges. She begins a routine that will not end until her own death, fanning water across the eggs to oxygenate them, brushing them clean with her arms to prevent fungal growth, and guarding them from the endless stream of small predators eager to snack on the developing young. This is not an act of conscious martyrdom, but a hormonal inevitability. Scientists studying these optic glands found that if the gland is removed, mothers can resume feeding and live months longer. Yet without the chemical cascade, the eggs are neglected and perish. The octopus is wired to burn out in the act of creation. By extinguishing her own life, she ensures the success of thousands of fragile offspring. In evolutionary terms, her genes march forward while her body collapses. This strategy, known as semal parity, is shared by salmon, mayflies, and certain plants, but in the octopus it is rendered more poignant by the animal's high intelligence. Here is a creature capable of puzzle solving, tool use, and even play, and yet her final chapter is dictated by an irreversible biochemical script. But the octopus is not always painted as a saintly mother. The dark twist of her life story comes in the moments before and around mating. In crowded dens where resources run thin, octopuses have been observed turning on one another, arms entwining not in cooperation, but in cannibalism. A smaller octopus that ventures too close may be seized and consumed, its body reduced to fuel for another's reproductive effort. Even during courtship, males risk their lives. A female may accept his sperm packet through a specially adapted arm, the hectocotylus, only to devour him moments later. This behavior is not consistent. Sometimes males escape, sometimes females ignore them entirely. But it is frequent enough to remind us that octopus intelligence is not built on human frameworks of empathy. Their cognition evolved to solve problems of survival in a world of predators and shifting seascapes, not to mirror mammalian notions of family or compassion. That intelligence is distributed in a way that challenges our very definition of a brain. Nearly 2/3 of the octopus's neurons reside not in the central brain, but in its arms. Each arm functions with a degree of autonomy, capable of sampling textures, tasting chemicals, and even deciding how to manipulate objects without central approval. When an octopus pounces on prey, spreading its arms like a living parachute over a crab or fish, the choreography is partly delegated to local decision-making in the limbs. This decentralization explains their extraordinary dexterity. An arm can open a jar, stack rocks, or weave a barricade of shells, while the central brain focuses on vigilance or camouflage. In effect, the octopus is less a single mind than a coalition of semi-independent processors working in concert. Evolution has created not just an animal, but a networked intelligence diffused across flesh. The arm's independence has fueled behaviors that verge on the surreal. In the wild, octopuses have been recorded dragging coconut shells across the seabed, later assembling them into makeshift shelters. Others barricade their dens with stones carefully arranged like doors to block entry. Some species use discarded shells as helmets, tucking their soft bodies inside to avoid predation. These examples hint at a form of tool use once thought unique to primates. Yet unlike a chimpanzee wielding a stick, the octopus does so with limbs that can both sense and decide. It is as though each arm is its own experimental lab, improvising solutions in real time. Still, even this flexible intelligence is subservient to the optic gland's inexorable command. The paradox is striking. The most behaviorally versatile invertebrate in the ocean is hardwired for a single path at the end of life. When the eggs finally hatch, After weeks or months of vigil, the mother is often a husk, skin slack, body weakened, movements lethargic. She dies soon after, consumed either by scavengers or by the sea itself. The young disperse as planktonic larvae, drifting upward into the currents where only a small fraction will survive. Her sacrifice is not gentle, but it is absolute. The story becomes even more complicated when humans enter the frame. Octopuses are increasingly studied in laboratories, where their intelligence and adaptability raise ethical questions. Can a creature that can solve mazes, recognize individual researchers, and manipulate its environment be treated as just another experimental animal? In some countries, octopuses now receive legal protections similar to vertebrates in research, acknowledging their capacity for complex behavior and possibly even forms of suffering that remain beyond our measurement. The debate grows sharper in aquaculture, where projects attempt to farm octopuses for food. Proponents argue it could reduce fishing pressure on wild populations, while critics highlight the cruelty of farming solitary, intelligent animals in dense enclosures where cannibalism and stress are inevitable. Unlike fish, octopuses cannot be easily penned without conflict. Their solitary, short-lived nature resists industrial scaling. These dilemmas remind us that the octopus occupies a strange liminal space in human perception. It is alien yet relatable, intelligent yet coldly pragmatic, a genius wired for sacrifice. When we look into the den of a brooding female, we see devotion that looks almost human. Yet when we widen the frame, we see behaviors, cannibalism, enforced self-starvation, that remind us we are peering into a logic not our own. To call it love or cruelty misses the point. Evolution has crafted a system that values the many over the one, the survival of thousands of offspring over the comfort of a single parent. Outside the cave, the ocean flows on. The crab that walked past earlier continues its foraging, unaware of the drama in the shadows. The mother fans her eggs, her arms moving in rhythm like the hands of a clock winding down. The pearls within will hatch, each a tiny replica of her kind, each carrying forward the possibility of another cycle of intelligence and sacrifice. She will never know them, never watch them grow. Her role is complete when theirs begins. The lesson left behind is stark. In the octopus, genius comes at a cost. The same flexible, distributed mind that engineers ambushes and invents tools is shackled to a hormonal script that demands self-destruction. What looks to us like devotion is, in truth, an evolutionary bargain, the surrender of the individual to secure the survival of the many. In the silent cave, among strings of glowing eggs, we glimpse not only the mystery of intelligence, but the weight of the code written into flesh. Night settles on the reef like a velvet curtain, blotting out the last streaks of fading light. The colors that dazzled in daylight, corals blazing in reds, yellows, and purples, now dissolve into muted shades of gray and green under the dim moonlight filtering through the surface. The reef does not sleep. Tiny shrimp click from crevices, plankton rise in drifting clouds, and hunting parties begin their slow patrols. Then, in the darkness of a narrow wall crack, something stirs. A slender head slides forward, eyes glinting like wet glass, jaws parted to reveal needle teeth. In an instant, the moray eel erupts from its hole, not with the snap of a normal bite, but with a surreal alien mechanism. A second set of jaws lances forward from deep within its throat, seizing a struggling fish and dragging it backwards into the waiting maw. It is a strike born not of brute force, but of evolutionary necessity, a solution to the problem of hunting in tunnels where retreat is impossible. The pharyngeal jaws of the moray eel are among the most remarkable adaptations in the ocean. Most fish possess them, small tooth-studded structures tucked at the back of the throat to help process food. But morays have turned this accessory into a weapon. Anchored within the throat, the pharyngeal jaws of a moray can extend forward like a spring-loaded harpoon, clamp prey with recurved teeth, and retract, pulling the victim into the digestive tract. This adaptation solves a critical challenge. Morays live and hunt in labyrinths of rock and coral, where ordinary suction feeding, the method used by most predatory fish to vacuum prey into the mouth, is impossible. In the confines of a crack, water cannot be displaced fast enough to create suction. The moray's innovation allows it to strike and hold without needing to back out or reposition. Once the prey is hooked by those hidden jaws, there is no escape. It is dragged into the gullet, whether wriggling or limp. The image is almost monstrous, but it reflects a perfectly tailored engineering solution to a life spent in shadows. But not every moray becomes a prize. For humans, eating these predators carries a risk as insidious as the eel itself. In tropical reefs around the world, a toxin called ciguatera lurks, born from microscopic dinoflagellates that grow on coral and algae. Small reef fish graze on these organisms, absorbing the toxin into their tissues. Larger fish then consume the grazers, and larger still consume them. With each step up the chain, the concentration of ciguatoxin accumulates, a process known as bioaccumulation. By the time it reaches apex reef predators, barracuda, groupers, and moray eels, the flesh can carry enough toxin to sicken or even cripple a human. The danger is not in spoiled meat. The fish can be fresh from the water, still twitching, and yet deliver an invisible dose that sends diners to the hospital. Symptoms range from nausea and neurological confusion to the bizarre reversal of hot and cold sensations, where a glass of ice water burns like fire on the tongue. Moray eels rank among the most notorious carriers of ciguatera. Their predatory lifestyle and long lifespan allow toxins to build to extraordinary levels. In some island cultures, the risk is so well known that morays are avoided entirely, considered cursed or taboo to eat. Fishermen who haul them in may throw them back, aware that the gleaming muscular body in their nets is more hazard than harvest. In other regions where tradition or necessity drives their consumption, outbreaks of ciguatera poisoning have been tied directly to moray flesh. This is one of the paradoxes of the reef. The very animals that embody stealth and predatory power can turn into toxic traps for humans. Unlike mercury in tuna, which can be measured, ciguatoxin offers no easy detection. Cooking does not destroy it. Freezing does not diminish it. To eat a moray is to gamble with chemistry written invisibly into its muscles. While their biology makes them fascinating, morays also live at the nexus of human curiosity and controversy. Few reef creatures generate as much fear and allure in divers as the sight of a moray eel's head protruding from acrovis, jaws gaping in what looks like a perpetual threat display. In truth, this open-mouth behavior is not aggression, but respiration. The eel pumps water over its gills by rhythmically opening and closing its mouth. Yet the image is arresting enough to inspire both reverence and reckless behavior. Tourism operators in some regions have built entire spectacles around feeding morays by hand, luring them out with chunks of fish to impress visiting divers. Videos of divers stroking the eels or coaxing them into open water for photographs spread easily online. But this practice carries risks both for humans and for the animals themselves. Morays that learn to associate divers with food can become bolder, even aggressive, biting hands that resemble bait. Their teeth are angled and sharp, capable of slicing through neoprene and flesh alike. Worse, conditioning alters natural behavior, pulling the eels from the security of their crevices into situations that can lead to injury or predation. Responsible dive guidelines increasingly discourage feeding, emphasizing observation over interaction. But in an age where digital clicks often outweigh ecological sense, the tension between education and entertainment remains unresolved. The moray eel is not only a solitary hunter, but sometimes a partner in an unlikely alliance. Across reefs in the Indo-Pacific, divers and researchers have documented cooperative hunts between morays and groupers, two predators with entirely different strategies. Groupers are pursuit hunters, powerful fish that can chase prey across open patches of reef, but their quarry often escapes into crevices too small for them to enter. Morays, by contrast, are ambush specialists, sliding into those same cracks with serpentine ease. Together, the two create a synergy that expands the kill zone of both. Groupers have been observed actively signaling to morays, performing headshakes or body shimmies that appear to serve as invitations. When the moray responds, the pair sweeps the reef in tandem. The grouper flushes prey into crevices where Thiel is waiting, or the eel drives prey out into the grouper's path. It is a partnership not born of altruism but of mutual benefit, one that demonstrates how intelligence and flexibility can emerge even in fish traditionally dismissed as instinct-driven. This cooperation challenges assumptions about the rigidity of fish behavior. The ability to recognize another species as a hunting partner, to respond to its signals, and to coordinate strategies suggests cognitive complexity that defies the notion of mindless instinct. It hints at evolutionary pressures where efficiency overrides boundaries, creating alliances of necessity. The reef, after all, is a battlefield of constant scarcity, where survival often belongs to those who innovate. By expanding their predatory reach through cooperation, morays and groupers demonstrate that strategy can transcend species. And yet in the human story, the moray eel remains a symbol of danger. Fishermen who pull one up by accident may hesitate to bring it aboard, wary of its thrashing coils and snapping jaws. Those who consider eating it risk more than just the bite. Divers who treat it as a prop-caught accidents that tarnish its reputation further. In every encounter, the eel embodies the paradox of the reef: beautiful, deadly, misunderstood. Its pharyngeal jaws reveal an evolutionary marvel, a solution to a problem of physics and habitat. Its flesh carries a hidden chemistry that punishes consumption. Its relationships with other predators reveal intelligence that bends the boundaries of expectation. The takeaway is stark. The moray eel is both assassin and poisoned prize. For the reef, it is a stealth regulator, shaping the fate of countless fish by striking from unseen corners. For humans, it is a cautionary lesson in biology's unpredictability. A catch that looks perfect on the deck of a boat may carry the legacy of microscopic toxins gathered over years, turning a meal into a medical emergency. The diver's photograph of a moray accepting food from a hand may hide the story of an animal conditioned to aggression. The partnership of moray and grouper whispers of cognitive depths we are only beginning to appreciate. In the end, the moray eel demands respect, not fear. To watch one emerge from its crevice under a sweep of moonlight, second jaws darting like a hidden blade, is to glimpse the elegance of an animal that has mastered the art of shadows. But to place it on a plate, to reduce it to spectacle, or to treat it as a harmless curiosity, is to miss the lesson it offers, that in the reef, every prize carries a price. The reef is settling into twilight, that brief suspension between the day's color and the night's darkness, when shadows stretch long across the coral heads. At the outer pass, where the lagoon spills into the open sea, the water pulses with a restless current. Fish begin their nightly migration. Plankton swarms rise from the deep, snappers gather in silvery clouds, and hunting jacks prowl the edges. Then, as if conjured by the tide itself, shapes emerge from the gloom. One by one they drift in from the deep blue, bulky bodies with mottled hides, broad heads and watchful eyes. Groupers, dozens of them, giants that seem too large to belong to such fragile reefs, glide into place along the promontory. This is not chance. It is ritual, played out with lunar precision. On this night, under this moon and tide, the groupers assemble to spawn. For a few hours, the wall is theirs. But above, the glow of boat lights breaks the surface. Nets hang ready. The hunters wait for their moment too. Spawning aggregations are the heartbeat of grouper survival, yet also their greatest vulnerability. For most of the year, these fish are solitary, each claiming a patch of reef or rocky overhang, fiercely defending it from intruders. But at specific times, often linked to the full or new moon, they abandon their territories and converge by the hundreds at exact sites along reef passes. The timing is astonishingly precise. Some species of grouper gather only a handful of times each year, with the largest aggregations collapsing into frantic bursts of spawning that last mere nights. Eggs and sperm are released into the rushing currents, fertilized in the water column, and swept out to sea to drift as larvae. The evolutionary logic is clear. By synchronizing their reproduction, the groupers overwhelm predators with sheer volume, flooding the water with millions of eggs. Yet this precision, once a survival advantage, has become their undoing in human-dominated seas. A single night of targeted fishing at these gatherings can wipe out years of reproductive effort. The problem is magnified by a twist in the grouper's life history: protogynous hermaphroditism. Many grouper species are born female and later change sex to become males once they reach a large size. It is a system that balances reproduction, ensuring that enough small individuals contribute eggs while a few dominant males fertilize them. But when humans enter the equation, the balance collapses. Fishermen prize the largest groupers for their size and market value. These big males are removed disproportionately, leaving aggregations dominated by females with no partners to fertilize their eggs. In effect, overfishing removes not just individuals, but the structural backbone of reproduction. Within a few seasons, the population crashes, unable to replace itself. What looks like a bountiful catch in one year becomes a vanishing act the next. The wall that once hosted giants goes quiet. This fragility is not hypothetical. Across the Caribbean and Indo-Pacific, records show how entire grouper fisheries collapsed after aggregations were targeted. Nassau groupers, once common, saw their numbers plummet when fishermen discovered their predictable gatherings. In some regions, the species is now endangered, surviving only where seasonal protections have been enforced. The tragedy lies in how quickly the decline can occur. Groupers live long lives, some for several decades, and their population dynamics depend on slow, steady reproduction. Remove a spawning aggregation for even a few years, and the lag in recovery can stretch into generations. Unlike fast-breeding reef fish, groupers do not bounce back with ease. The timing that once guaranteed resilience now guarantees vulnerability, and yet their gatherings are not silent affairs. Beneath the water during these spawning events, divers and hydrophones have recorded the resonant booms of groupers. These sounds, produced by muscular contractions of the swim bladder, serve as communication, cues that signal readiness to spawn, mark territory, or coordinate movements. Each aggregation site resonates like an underwater drum circle, the low-frequency pulses carrying across the reef. These sounds are not random. Groupers return to the same promontories year after year, guided by fidelity as strong as the instinct that drives salmon back to rivers. A site may host spawning for centuries, shaping not just grouper survival, but the entire rhythm of the reef community. When those sounds stop, when the aggregation vanishes, it is as if a piece of the reef's identity disappears with it. Conservation efforts that focus on protecting these sites, through seasonal closures that ban fishing during spawning windows, have shown remarkable success. Where closures are enforced, aggregations rebound, the booms return, and the reef regains its balance. But the dangers of grouper consumption are not limited to population collapse. Large, old individuals often accumulate mercury in their tissues, a consequence of bioaccumulation similar to that of ciguatoxin in moray eels. As apex reef predators, they consume a wide array of smaller fish over decades, slowly absorbing heavy metals released into the ocean from human industry. By the time a grouper reaches the size that commands a high price on the market, its flesh can carry mercury levels that pose risks to human health. The irony is sharp. The fish most celebrated for their bulk and rarity are often those least safe to eat in quantity. Public health warnings about mercury usually focus on open ocean predators like tuna or swordfish, but groupers share the same hazard in coastal ecosystems. Yet this message rarely reaches local markets or tourist restaurants, where large groupers are still displayed with pride. The tale of the grouper is thus layered with contradictions. It is a fish of power and longevity, a reef wall owner that commands territory with bulk and force. It is also a fish of vulnerability, undone by the very precision of its life cycle. Its reproduction is a marvel of synchrony, yet that synchrony exposes it to human exploitation. Its sounds echo across centuries of reef continuity, yet those echoes can vanish in a few seasons of over-harvesting. Its flesh can nourish, but also carry toxins accumulated from human pollution. The grouper embodies the paradox of reef giants: strength that hides fragility, abundance that can collapse into absence. To see a grouper aggregation is to glimpse a spectacle few now witness. As dusk deepens, males patrol the gathering, their colors intensifying into courtship displays. Females swell with eggs, circling in nervous bursts before releasing clouds into the current. The water becomes a blizzard of life, particles glowing in shafts of moonlight, swept away toward the deep. Sharks and jacks circle the periphery, snatching stray fish or feeding on eggs, but the majority escape, carried beyond the reef into the vast nursery of the ocean. It is an ancient performance, repeated long before humans placed nets above it. Yet in places where boats wait with lights, where the aggregation is intercepted before the dance begins, the scene never unfolds. The fish are gone, the reef silent, the wall empty. The takeaway is sobering. To take the wall owner on the wrong night is not just to remove a fish, it is to silence a tradition of reproduction that sustains the reef. One night of greed can erase decades of balance, leaving the ecosystem to falter in the absence of its guardians. The grouper teaches us that survival is not only about strength or size, but about timing, trust in cycles, and fidelity to place. Protect those cycles, and the reef will resound with the booms of giants. Break them, and a living wall becomes nothing more than barren rock. The morning fog drapes low over a kelp forest off the California coast, softening the boundary between sea and sky. Sunlight filters through in pale shafts, striking the glossy fronds of giant kelp that sway like cathedral pillars in the swell. Amid the drifting forest, a familiar sight bobs on the surface, a sea otter lying on its back, belly up, fur glistening in the pale light. In its paws it cradles a rock, which it brings down rhythmically upon a spiny sea urchin. The sound carries faintly through the still air, the crack of shell against stone. A moment later, the otter munches contentedly, pink tongue flashing as it pulls out the urchin's tender insides. It is an image that has charmed millions, the playful toolsmith, furry and buoyant, cracking shells in the sun. Yet beneath this endearing surface lies a predator with sharp edges, an animal that engineers ecosystems, disrupts fisheries, scars its own kind, and, when hunger presses, turns to unexpected prey. The sea otter is not simply a charismatic mammal, it is a keystone predator. In the coastal ecosystems of California, Alaska, and parts of the North Pacific, its appetite determines the fate of entire forests. Left unchecked, sea urchins graze ravenously on kelp holdfasts, mowing down lush underwater meadows into barren seascapes. But when otters are present, they crush and consume urchins by the dozens, holding the population in balance. The effect cascades outward. Healthy kelp forests bloom, providing habitat for countless fish, invertebrates, and seabirds. Carbon is sequestered in the thickening fronds, coastal erosion is softened by the dense beds, and biodiversity thrives. Remove the otter, and the forest collapses into desert. Protect the otter, and the forest returns, as if stitched back together by the teeth of the animal cracking shells on its belly. The story of kelp recovery along the Pacific coast is inseparable from the return of sea otters, a living example of how a single predator can shape entire ecosystems. Yet the portrait of the otter as a gentle savior hides aspects that make people uneasy. Their mating system is not tender. Males pursue females with aggressive persistence, often grasping them by the face with teeth during copulation. Scars on the noses and muzzles of female otters testify to this roughness, a reality that jars against their playful public image. More unsettling still are rare observations of otters attacking animals outside their usual diet. When prey is scarce, individuals have been documented harassing and killing small harbor seals, sometimes dragging them into the kelp and consuming parts of their bodies. There are even accounts of otters preying upon seabirds such as gulls and cormorants, dismantling them on the water's surface with the same dexterity they apply to clams. These events are not the norm, but they serve as reminders that otters are not passive charmers. They are opportunistic carnivores whose sharp teeth and relentless metabolism can drive them into behaviors that disturb our carefully curated image of cuteness. That metabolism is the central fact of their lives. Unlike seals or whales, sea otters lack blubber. Instead, they rely on the densest fur in the animal kingdom, as many as 1 million hairs per square inch, layered to trap air and insulate against the chill of the Pacific. but such fur comes at a cost. Without fat reserves, otters must feed almost constantly to fuel their high metabolic rate. An adult may consume up to a quarter of its body weight in food each day. This relentless hunger explains much of their behavior. It drives their constant foraging, their innovation with tools, and their willingness to expand their menu when resources thin. It also explains their occasional conflicts with humans, for they target the same shellfish that people prize: abalone, crabs, clams, and sea urchins. The tension between otters and humans has played out dramatically along North American coastlines. After centuries of fur hunting nearly drove otters to extinction, conservation programs reintroduced them to parts of their former range. Their return revitalized kelp ecosystems, but also reignited conflict with coastal fisheries. Commercial shellfish harvesters saw their catches dwindle as otters reclaimed ancestral feeding grounds. In Alaska, some communities argue that otters decimate valuable crab populations. In California, abalone divers complain that otters leave little behind. The challenge for managers has been to balance ecological restoration with economic survival. Some regions have experimented with balanced harvest zones, where otters are allowed full dominance in certain areas to restore ecosystems, while humans retain exclusive access in others. The debate remains heated, a reminder that conservation is never just about biology, but also about livelihoods and values. Beyond these conflicts lies another dimension: the otter's remarkable role as a cultural and scientific symbol. To coastal indigenous peoples, otters were historically both a resource and a spirit figure, woven into traditions that balanced use with reverence. To scientists, they are a case study in trophic cascades, textbook examples of how top predators regulate ecosystems in ways invisible until they are gone. To the general public, they are internet darlings, their expressive faces and playful habits inspiring affection far beyond the coasts they inhabit. Yet this broad spectrum of meanings complicates their conservation. Policies must navigate not only ecological facts, but also emotional attachments, historical injustices, and modern economic pressures. When viewed underwater, the contradictions of the sea otter sharpen. In the kelp canopy, an otter spins and dives, its body slender and agile, paws probing for crabs beneath rocks. A pouch of loose skin under its forearm holds collected tools and food, a built-in shopping bag that turns foraging into a mobile enterprise. At the surface, it cracks shells against stones balanced on its chest, an image of ingenuity that recalls primates more than typical marine mammals. Yet the same animal, if deprived of clams, may turn its skills toward unsuspecting gulls, tearing feathers aside with unsettling efficiency. This duality of toolsmith and opportunist, ecosystem savior and predator of convenience is what defines the sea otter. Their story also intersects with climate and conservation in unexpected ways. As kelp forests vanish under the twin pressures of warming oceans and unchecked urchin populations, otters emerge as unlikely climate allies. By controlling urchins, they allow kelp to rebound and store carbon. Estimates suggest that healthy otter-anchored kelp forests can sequester millions of tons of carbon dioxide, a service of global significance. Thus, protecting otters is not only about saving a species or a landscape, but about influencing the chemistry of the atmosphere itself. Yet these benefits rely on acknowledging their full reality: creatures that bite, scar, and raid, as well as creatures that charm, cuddle, and restore. In the end, the sea otter defies simple categorization. To see one floating on its back, paws folded across its chest, fur haloed in sunlight, is to witness innocence incarnate. To watch the same animal tear into a bird with ruthless precision is to confront the predator behind the fur. Neither image is false. Both are facets of a species that lives on the edge of survival, driven by hunger, honed by evolution, and entangled in human history. The takeaway is unavoidable. The internet's favorite marine mammal is also a hard-edged predator, a keystone force whose appetites must be managed alongside our own. To reduce the sea otter to a plush mascot is to miss the truth. Its genius lies in the tension between softness and steel. It is both engineer of kelp forests and competitor at the shellfish table, both symbol of recovery and source of conflict. To conserve it, is to accept not just its charm, but its complexity. The sea is a cathedral this morning, shafts of light streaming down through turquoise water to illuminate a congregation of life gathered around a coral promontory. Tiny cleaner wrasses dart in and out of the folds of parrotfish, surgeonfish, and trevallies. Then, as though choreographed for spectacle, a shadow sweeps across the reef. Broad wings spanning more than 5 meters glide into the clearing with effortless grace. A manta ray drifts above the coral, slowing as if suspended by invisible wires, and settles into the ballet of a cleaning station. Wrasses swarm over its enormous body, picking at parasites, grooming delicate gill flaps, even darting into the cavernous mouth before slipping back out. The manta hovers patiently, each flick of its cephalic lobes adjusting its position with fluid precision. It is a scene of serenity, the angel of the sea suspended in ritual care. And then, beyond the reef, reality intrudes. A ghost net hangs in the current along a migratory corridor, silent and invisible, until a ray blunders into it. What minutes earlier was grace becomes struggle, wings thrashing, body twisting, a giant ensnared by threads designed not for angels, but for profit. The price on manta rays lies not in their meat, which is tough and of little culinary value, but in their gills. Along parts of Asia, demand for dried manta gill rakers, the fine comb-like structures they use to filter plankton from seawater, has grown under the banner of traditional medicinal use. Marketed as cures for ailments ranging from chickenpox to infertility, these rakers are harvested by the kilogram, dried and sold at high prices despite lacking scientific evidence of efficacy. For hunters, the economics are simple. One manta can yield kilos of rakers worth far more than the rest of its body. For the species, the consequences are dire. Mantas reproduce slowly. Females give birth to a single pup after a gestation of more than a year, and they may only reproduce once every few years. Populations cannot sustain even moderate levels of targeted harvest. When a fishing community turns to mantas, declines are swift, recovery glacial. A net set across a migratory highway can erase decades of careful balance in a single season. Even in places where mantas are not hunted directly, they face threats of a more insidious nature, the dust of our industrial world drifting invisibly into the sea. Mantas are filter feeders, sweeping through ocean fronts where plankton blooms gather in rich abundance. Yet those same convergences now accumulate microplastics, fragments of synthetic fibers, beads, and particles shed from clothing, packaging, and tire dust. Each gulp of plankton carries with it not only the food that fuels a giant's glide, but also threads of polyester and polyethylene. Laboratory studies show mantas ingesting significant amounts of microplastic daily, with particles found lodged in their gills and digestive tracts. While research continues to unravel the long-term effects, early signs are sobering: inflammation of tissues, reduced nutrient absorption, and potential transfer of toxins into the bloodstream. For an animal already pressed by slow reproduction and targeted trade, the slow poisoning of its feeding grounds adds yet another layer of vulnerability. Yet mantas are not passive victims. Their hydrodynamic design is a marvel of engineering, honed by millions of years of evolution to make their filter feeding not only possible, but efficient on a massive scale. At the front of their heads, cephalic lobes unfurl like guiding hands, funneling water into their cavernous mouths. Inside, gill rakers form not simple sieves that would clog with plankton and debris, but intricate ricochet separation systems. Water flows in precise vortices that deflect particles toward capture while allowing clean flow to exit. It is a design principle that engineers study to model new filtration technologies, a biological innovation that allows mantas to process thousands of liters of water per hour without fouling their filters. But this system has a vulnerability. It requires clean flow. Too much silt, plastic fiber, or suspended waste, and the hydrodynamic miracle falters. In that sense, mantas are more than just charismatic giants. They are indicators of the sea's clarity. When mantas feed well, the ocean's balance remains intact. When their filters choke, it signals something far larger has gone wrong. Tourism has become a double-edged sword in the manta's survival story. In many regions, the economic value of live mantas far outweighs their worth as dried gills. Divers and snorkelers flock to cleaning stations and feeding fronts for the chance to hover beside them, and entire communities now depend on manta tourism for livelihoods. Yet even this apparent salvation carries risks. Cleaning stations are bottlenecks, places where mantas must pause, sometimes daily, to maintain their health. Crowds of divers descending too close can disrupt the ritual, startling mantas away before cleaning is complete, leaving them with heavier parasite loads and added stress. Behavioral studies show mantas altering their visitation frequency at heavily trafficked stations. The solution is simple but not always enforced, maintaining respectful distances, limiting group sizes, and managing boat traffic. Where these rules are observed, mantas and humans coexist in a balance that enriches both. Where they are ignored, the stations degrade from sanctuaries into stress points. The paradox is striking. Around the world, communities face a choice between the quick profit of killing a manta for its gills and the long-term wealth of protecting it for tourism. The numbers favor protection. A single manta can generate hundreds of thousands of dollars in tourism revenue over its lifetime, supporting boat operators, dive guides, and hotel owners. Yet for hunters living on the margins, the immediate payout of a catch can outweigh distant promises of sustainability. Conservation must therefore operate not just on biology, but on economics, building incentives that align human survival with manta survival. Where marine protected areas, seasonal closures, and enforcement exist, manta populations stabilize and even grow. Where they do not, the nets drift and the angels vanish. Beneath the wings of a manta ray lies an evolutionary gamble that mirrors these human dilemmas. To invest in few offspring with high survival odds rather than many with lower ones. Each pup is born live, rolled out from the mother's body already several feet wide, ready to swim and feed. The investment is immense, the odds calculated on the assumption of long lifespans and safe migrations. But with hunting, nets, and pollution, that gamble becomes precarious. One lost adult is not just a single animal gone, but decades of potential reproduction erased. Populations fragment, genetic diversity dwindles, and recovery stretches far beyond the scale of human patience. To hover beside a manta in clear water is to feel the paradox in your bones. Its wings beat slowly, almost imperceptibly, yet it moves with more grace than any machine could replicate. Its eye meets yours, not with mammalian warmth, but with a steady alien calm, as though measuring your presence. For a moment, the ocean feels ordered, timeless, anchored by the slow passage of this giant. And yet, just beyond the reef, a drifting net waits, a plastic haze rises, and markets still weigh gills by the kilogram. The takeaway is clear. Mantas are angels, but angels with a price on their gills, forced to navigate a world where their grace is undervalued and their survival uncertain. They embody the contradictions of our era, worshipped in tourism brochures, hunted in remote markets, poisoned by particles too small to see. To save them is to reckon with how our dust, plastic, chemical, economic, spreads across the sea. Protect the corridors, regulate the markets, manage the encounters, and the ballet at the cleaning station will continue. Fail, and the water will empty, the reef will quiet, and the angels will be gone. The tide drifts gently over a meadow of seagrass, blades swaying in the filtered sunlight like green ribbons in an unseen breeze. Tiny bubbles rise from the sand, and among the blades, shapes emerge that are easy to miss at first. A pair of seahorses, their bodies bent in elegant curves, hover upright in the water, tails coiled tightly around stems for anchor. Their movements are delicate, almost ornamental, as if designed for invisibility. Then something extraordinary unfolds. The male shudders, his abdomen swelling, and from a small opening in his brood pouch, a shimmer of fry bursts forth, each no bigger than a grain of rice. The newborns scatter into the water column, glinting like sparks before vanishing into the grass. It is one of the rarest spectacles in the animal kingdom. Male pregnancy, where fathers give birth to living young. Yet in another scene, far from this quiet meadow, Sacks of dried seahorses lie stacked in a customs warehouse, seized at a border crossing. Millions are taken every year for medicine, souvenirs, and curios, their lives reduced to commodities. The most romantic fish in the ocean lives a double existence, celebrated in myth and love, but quietly trafficked by the million. Male pregnancy in seahorses is not a curiosity, but a sophisticated adaptation. The brood pouch of a male functions in ways strikingly similar to a mammalian placenta. After a female deposits her eggs into the pouch, the male fertilizes them internally. The pouch then grows a vascular network that delivers oxygen, regulates salt and ion balance, and even provides nutrients to the developing embryos. Hormones surge through the male's body, reshaping metabolism to sustain the growing brood. In effect, he becomes a womb. For weeks, he tends the developing fry, expelling them only when they are ready to face the world on their own. This unusual inversion of roles is thought to have evolved as a way to maximize reproductive efficiency. With males carrying the burden of gestation, females are freed to mature additional clutches of eggs, increasing the reproductive output of the pair. But success depends heavily on pair bonds. Seahorses are one of the few groups of fish that often form monogamous partnerships, sometimes lasting for an entire breeding season or longer. Daily greetings, small dances, synchronized color changes or tail twining reinforce these bonds, ensuring reproductive timing aligns. A strong partnership improves the odds of fry survival. Break the bond and the cycle falters. Yet for all the delicacy of their reproduction, seahorses face pressures that no courtship ritual can defend against. Each year, tens of millions are removed from the ocean. Many vanish as bycatch, swept up in trawl nets that scrape seafloors for shrimp and fish. Others are harvested deliberately for use in traditional medicines, where dried seahorses are ground into powders or steeped in tonics, marketed as treatments for asthma, impotence, or general vitality. Still others are sold as curiosities, souvenirs for tourists, or decorative items for aquaria. The global trade has been traced through hotspot nations and shipping routes. Southeast Asian fisheries supplying dried seahorses that move through hubs in Hong Kong and mainland China. West African catches exported across the Atlantic. Even small-scale harvests in Latin America entering global streams. Though international agreements like CITES list seahorses under trade restrictions, enforcement lags and seizures reveal the scale of the shadow market. The shimmer of fry in a seagrass bed is mirrored by mountains of dried bodies in sacks, millions upon millions of small lives erased. The loss is not only numerical, but ecological. Seahorses depend on habitats that are themselves under siege. Seagrass meadows and mangrove forests serve as nurseries, offering both camouflage and feeding grounds for these slow, weak swimmers. But across the tropics and subtropics, these habitats are being degraded or erased. Coastal development, aquaculture ponds, and pollution have eliminated vast tracts of seagrass and mangrove. Without the blades to cling to or roots to hide among, seahorses drift exposed, vulnerable to currents and predators. Restoration efforts, however, have shown promise. In places where seagrass has been replanted or mangroves protected, seahorses return, anchoring themselves once more in the regrown shelters. These projects demonstrate how conserving habitats benefits not just the high-profile ecosystems of coral reefs or rainforests, but the quieter, overlooked meadows where small dramas of reproduction unfold. For seahorses, habitat is destiny. Remove the nursery and no pouch or pair bond can compensate. The rise of aquaculture has been proposed as a solution, offering captive breeding as a way to reduce pressure on wild populations. Seahorses can indeed be bred in tanks, and some programs supply individuals for the aquarium trade, theoretically easing the need to harvest from the wild. But the picture is complicated. Captive breeding can inadvertently feed demand rather than replace it. By making seahorses more accessible, it risks normalizing their purchase as pets or curios, increasing total consumption. Moreover, breeding programs often struggle to replicate the ecological complexity of wild systems. Mortality among fry is high, diets must be carefully managed, and genetic diversity can be low. In some cases, Aquaculture has even been used as a cover for laundering wild-caught seahorses into legal trade. Thus, while aquaculture holds potential, it cannot serve as a panacea. The deeper challenge lies in reducing demand altogether, shifting cultural practices, and enforcing protections that keep seahorses in the sea rather than in sacks. To watch a seahorse in its natural setting is to see the fragility behind the statistics. Its body, armored in bony plates, bends in a permanent curve, tail coiling around a grass blade as currents sway. Its head tilts downward, horse-like, as it uses a tubular snout to suck in tiny crustaceans with a swift vacuum snap. It moves not with speed but with patience, drifting upright, propelled by the flutter of a dorsal fin too small for haste. Every detail speaks of a life adapted not for aggression or resilience, but for stealth and subtlety. This makes the scale of human exploitation all the more jarring. The animal that survives by invisibility is made hyper-visible in trade, stripped of its camouflage and dried into bulk. The story of the seahorse, then, is one of paradox. It is a fish that embodies romance, where males give birth and pairs form bonds that echo human ideals of partnership. It is also a commodity, trafficked in numbers so vast they defy imagination. Its habitats are vanishing even as its symbolic power grows. Its future may depend not only on marine biology, but on shifting human values, whether we see the seahorse as medicine, ornament, or miracle of evolution. The takeaway is clear. The most romantic fish is quietly trafficked by the million. Saving it will require more than awe at its peculiar biology. It will demand habitat restoration, strict enforcement of trade restrictions, and cultural shifts that reduce demand. Only then will the sight of a male giving birth in a shimmer of fry remain a spectacle of life, not a memory overshadowed by the weight of dried bodies in sacks. The sea boils with life as a line of penguins arcs in unison through the surf. Their sleek bodies cut through the water like living torpedoes, porpoising in bursts of speed that carry them toward the shoreline. Each leap is jubilant, a rhythm born of both necessity and momentum as they vault from wave to wave. Then, with a final surge, they land clumsily on the beach, shaking off spray as they shuffle upright and join the throngs already gathered on land. The air is filled with noise, braying calls, sharp cries, the endless drone of thousands of voices woven into a single cacophony. It is a scene that at first glance radiates joy, reunion, and community. Yet beneath this surface lies a harsher truth. In the chaos of the colony, neighbors eye one another with suspicion. A penguin returning from sea may carry food in its gullet, or worse, reveal a chick at its feet. For those whose own breeding attempts have failed, temptation lingers. The act shocks human observers, but in the penguin world, chick kidnapping is a reality. The colony's structure is one of relentless arithmetic, every action weighed against energy and chance. Penguins that have lost their eggs or chicks sometimes attempt to adopt, or abduct, the young of others. The motives are not always clear. Some biologists suggest it is an expression of overwhelming parental drive, hormones still surging with the urgency to nurture even after failure. Others see it as a desperate attempt to salvage reproductive investment in a world where success rates can be brutally low. Whatever the reason, the act unfolds in a haze of chaos. A chick may be pulled between two adults, pecked or trampled in the scuffle. Most kidnappings fail, the chick either abandoned or lost. To human eyes, it looks cruel, even deranged. But to the penguin colony, it is another variable in the math of survival. Not every chick can live, not every bond endures. The harsh calculus of limited food, harsh climate, and predation is written across every interaction. The ground itself tells part of this story. Penguins live amid a sea of guano, their excrement layering thick across rocks and ice, staining the landscape in streaks of pink, brown, and green. It is more than an aesthetic assault. Guano accumulations release nitrous oxide, laughing gas, in volumes large enough to be detected in the atmosphere above colonies. Scientists measuring the plumes have described the effect with ironic humor, but the chemistry is real. Penguins, by sheer density of numbers, alter the air itself. These plumes are not trivial curiosities, but potent greenhouse gases, adding to the complexity of the Antarctic system. What appears as comic detail, the tuxedoed birds fouling their own stage, is part of a broader pattern in which even their waste feeds into climate dynamics. Nutrient-rich guano also fertilizes surrounding ecosystems, supporting blooms of algae and microorganisms. The penguin colony then becomes both a biological furnace and a chemical reactor, its emissions stretching influence beyond the beach. But the greatest pressure on penguins comes not from their guano or their quarrels, but from the sea. Their existence is bound to krill, the tiny crustaceans that swarm in vast shoals across polar waters. Krill feed on phytoplankton under the sea ice, and penguins feed on krill. The chain seems simple, but it is fragile. As sea ice shrinks with warming temperatures, the algae that nourish krill diminishes. At the same time, commercial fisheries have increasingly targeted krill, harvesting them for aquaculture feed, omega-3 supplements, and industrial products. The result is a squeeze: less krill in the water, more mouths competing for what remains. For penguins, this transforms the arithmetic of parenting. Adults must travel farther to find food, spending more energy while chicks wait hungry on land. The longer the commute, the more likely the chick weakens and dies before the next meal arrives. Colonies that once thrived on abundant krill face sharp declines when these food belts shift. What seems like a minor adjustment, an extra few kilometers of swimming, can tip the balance fatally in a system where energy margins are already razor-thin. Predators add another layer to this balancing act. Leopard seals lurk at the edges of penguin highways, waiting for the moment when a bird breaks formation or lags in its porpoising rhythm. With jaws powerful enough to shear bone, they take their share of returning adults. Skua gulls circle above the colonies, swooping down to snatch unattended eggs or vulnerable chicks. These predators are not intruders, but participants in the system. Their presence shapes penguin behavior. Colonies hedge their bets by sheer scale, timing hatching so that thousands of chicks emerge in synchrony, overwhelming predators with more potential meals than they can possibly consume. Some species nest on cliffs or ice shelves that reduce access to ground predators, trading convenience for security. Others rely on camouflage, chicks blending into the guano-stained rocks to escape aerial detection. The result is a dynamic equilibrium where predator and prey shape one another's strategies. The penguin's losses to seals and skuas are not failures, but part of the cost of maintaining the colony as a whole. In this light, penguins are less symbols of joy than of relentless efficiency. Every gram of energy counts. Parents shuttle fish loads back from the sea in precise measures, regurgitating to chicks whose growth curves are finely tuned to the rhythm of adult foraging. Fail to deliver enough and the chick falls behind. Succeed and the cycle moves forward. The colony amplifies both success and failure, magnifying gains and losses across thousands of pairs. It is a system where exuberant displays of courtship, tender care for chicks, and shocking acts of theft or neglect are all facets of the same underlying calculus. The tuxedo may charm us, but beneath it is an accountant tallying the ledgers of life. For humans, penguins are icons of innocence, their upright stance and clumsy waddles masking the harder truths of their ecology. But understanding them demands confronting these truths. Kidnapping attempts, guano emissions, food scarcity and predation are not aberrations, but intrinsic parts of penguin existence. They remind us that the colony is not a paradise of cooperation, but a crucible of survival. And in the context of climate change and industrial exploitation, the math grows darker. With sea ice shrinking and krill fisheries expanding, the balance tilts ever more steeply against them. Colonies once secure may collapse not because of seals or skuas, but because of human choices written in fishing quotas and carbon emissions. And yet, resilience persists. In places where krill harvests are managed carefully and marine protected areas shield key feeding grounds, penguin populations stabilize. Conservation shows that the dark math can be bent towards survival if the variables are adjusted. The colony remains a place of noise, struggle and competition, but also of continuity. Generations linked through the arithmetic of survival. The challenge is whether we can recognize the cost of every gram of energy, not just for penguins, but for the ecosystems that depend on them. The takeaway is stark. Beneath the tuxedo is no comic caricature, but a brutal accountant, calculating survival with precision. Each leap through surf, each stolen chick, each regurgitated fish is part of a balance sheet written against the backdrop of ice, krill, and predators. The joy we project onto penguins is real, but it is only half the story. The other half is a ledger of gains and losses in which nothing is wasted, nothing is free, and every choice carries weight. On the shallow reef, where the tide retreats and exposes sand flats littered with coral rubble, a crab scuttles sideways across the uneven ground. Its shell is a fortress, legs armored, claws held ready to grasp or defend. It pauses beneath the shelter of a branching coral, antennae twitching, eyes swiveling on stalks to scan the territory. At first glance, this crab is the image of resilience, quick, armored, endlessly adaptable. Yet within its body, hidden beneath the hard carapace, another life form can already be at work. A parasite threads through its tissues, reshaping its physiology and even its behavior. The crab may appear healthy, but in truth it is no longer its own master. It is being transformed into a zombie, castrated and compelled to rear not its own young, but the offspring of its parasite. The culprit is Sacculina, a genus of rhizocephalan barnacles whose life cycle is as grotesque as it is effective. Unlike the barnacles familiar to sailors, shell-encrusting sedentary filter feeders, Sacculina has abandoned its crustacean form entirely. It begins as a tiny larva drifting through the water until it encounters a crab. There it injects cells into the host, which creep through tissues like an invasive root system. Within weeks, the parasite hijacks the crab's endocrine system, halting the production of sex hormones. Reproduction is shut down. Testes or ovaries atrophy. The crab, whether male or female, is rendered sterile. Then the parasite grows an external reproductive sac that protrudes from the crab's abdomen, mimicking the egg mass of a female crab. The host, stripped of its own biological purpose, now guards and tends this sac as though it were its own brood. Males cradle the parasite's offspring as if they were mothers, fanning water across the sac and cleaning it of debris. In evolutionary terms, Sacculina has performed the ultimate takeover. It has reprogrammed the crab's instincts to serve its own reproductive agenda. For the reef, this drama is invisible unless closely inspected, yet its consequences ripple across populations. Parasitized crabs are removed from the breeding pool, reducing the number of fertile individuals. In some heavily infested regions, large percentages of crab populations are sterilized, altering the ecological roles they play. The parasite is not simply a burden on a single individual, but a quiet manipulator of the balance between predator, scavenger, and prey. It is a reminder that even the toughest shells conceal vulnerabilities that evolution has found ways to exploit. Yet not all crab stories are tales of horror. In the quieter corners of the reef, another drama unfolds, one of barter, competition, and recycling. Hermit crabs, unlike their armored cousins, lack full protective shells of their own. Instead, they commandeer the empty shells of snails, using them as mobile fortresses. But these shells are finite, and competition is fierce. A single abandoned shell can set off a chain reaction as hermit crabs line up, forming what biologists call a vacancy chain. The largest crab takes the new shell, leaving its smaller shell behind for the next in line, and so on down the queue. In effect, the crabs operate a barter economy in which housing is passed through the community, preventing waste and ensuring that shells are continuously recycled. These chains can involve half a dozen crabs or more, each upgrading in sequence in a matter of minutes. It is a remarkable display of collective opportunism. The survival of the group hinges not on cooperation in the mammalian sense, but on individual self-interest that nonetheless benefits all. This shell economy reveals how crabs knit themselves into the reef's cycles of use and reuse. Nothing is wasted. A shell that once housed a snail becomes a hermit's armor, then, as it erodes, perhaps a refuge for a worm or sponge. Through these chains, crabs maintain the flow of resources across the ecosystem. They are not predators in these moments, nor prey, but participants in a market as old as the reef itself. For human observers, the sight can verge on comic, crabs squabbling, tugging, lining up in a shuffling dance of sideways motion. Yet it is also profound. The vacancy chain exemplifies how even small creatures shape efficiency within ecosystems. Beyond parasites and shells, crabs perform another function essential to reef survival. They are custodians. As detritivores, many crab species feed on decaying plant and animal matter, algae and leftover scraps. In doing so, they break down complex organic matter into smaller fragments that microbes and other organisms can further decompose. This shredding service accelerates nutrient cycling, ensuring that energy locked in carcasses or plant debris is rapidly returned to the ecosystem. Without such cleanup crews, reefs would choke on their own productivity, clogged with waste that could harbor pathogens or stifle new growth. By scavenging and shredding, crabs sustain the nutrient loops that allow coral polyps to thrive, seagrass to spread, and fish populations to replenish. Their role as janitors is unglamorous, but without it, the dazzling spectacle of a healthy reef would collapse under its own weight. Yet even these janitors are not spared the unintended traps humans leave behind. Crab fisheries around the world rely on baited pots and traps, designed to lure crabs inside with the promise of food. Many of these traps are lost or abandoned, drifting on the seafloor as ghost gear. Their entrances remain open, their baits replenished naturally by the bodies of those that die within, creating a cycle of endless capture. Crabs wander in, feed, perish, and become bait for the next victim. In some regions, thousands of such ghost traps continue killing silently for years. The efficiency that crabs once lent to reefs is turned against them, their natural opportunism exploited by a machine that never stops. Efforts to combat this include biodegradable trap designs that break down after weeks, but adoption is inconsistent. For now, the reef's custodians are caught in a paradox. They recycle life's waste, yet are themselves wasted by technology unmoored from responsibility. Taken together, the story of crabs is one of duality. They are armored survivors, yet vulnerable to parasites that hijack their very identities. They are competitors, yet their competition builds economies of recycling that sustain entire communities. They are cleaners, shredders, and recyclers, yet victims of traps that never rest. They embody the contradictions of reef life, where survival depends not only on strength but on flexibility, not only on armor, but on adaptation to forces as small as a parasite's cell and as large as industrial fishing. To watch a crab on a reef is to glimpse these tensions condensed into a single sideways scuttle. It may pause to pick detritus from the sand, serving as janitor. It may wrestle with another over a shell, playing the role of trader. It may carry, unbeknownst to the casual observer, the alien roots of a parasite dictating its every move, a zombie enslaved. Crabs are at once individuals and instruments of larger forces, their stories branching from the smallest crevice to the global seafood markets that pull them into traps. The takeaway is clear. Crabs are both the reef's janitors and its victims, both free-living custodians and puppets of zombie biology. Their fates intertwine with parasites, predators, shells, and nets, each thread tugging at the balance of reef life. To dismiss them as simple scuttling creatures is to overlook their roles as engineers, recyclers, and unwilling hosts in dramas more complex than any armor suggests. Beneath the hard shell lies a ledger of debts and bargains written in hormones, shells, and scraps, a testament to the complexity that sustains the reef. On a rocky shoreline, the tide withdraws to reveal a carpet of mussels clamped tight against one another, their shells glistening with spray. To most creatures, these armored bivalves are fortresses, locked shut by powerful adductor muscles, impervious to all but the most determined predators. Yet from beneath the waterline, a slow, patient advance begins. A starfish creeps forward, hundreds of tube feet extending and retracting in coordinated waves. It is not a sprint, but a siege. Reaching the mussel, the starfish latches on, its arms arching around the shell. Then, in an act that defies vertebrate conventions of feeding, it everts its stomach, pushing the soft, pale organ through its mouth and into the narrow gap between the muscle's shells. Digestive enzymes flood the space, liquefying the flesh inside. Hours later, the stomach retracts, pulling the digested meal back into the starfish's body. The muscle's armor has been bypassed not by force, but by the patient innovation of external digestion. In slow motion, the starfish becomes a living sledgehammer, prying open the locks of the reef and reshaping the balance of who thrives and who vanishes. The mechanics of this predation are as remarkable as they are alien. Starfish lack centralized brains, yet they coordinate thousands of tube feet with surprising precision. Each foot is operated by a hydraulic system, seawater drawn into a network of canals pressurized and released to extend or contract. Sensory cells at the tips detect chemicals and light, guiding the starfish toward prey. Coordination emerges not from a single command center, but from a decentralized nerve net that runs along the arms. It is as though each arm thinks locally, negotiating its movements with neighbors until the whole animal lurches forward in consensus. This distributed intelligence gives starfish resilience. Cut off an arm and the remaining arms continue functioning, sometimes regenerating the lost limb entirely. The body is both organism and coalition, an arrangement that reflects the ocean's tendency to favor systems over individuals. Yet the role of starfish extends far beyond the fate of a single mussel. In intertidal ecosystems along the Pacific coast of North America, the ochre sea star serves as a keystone predator. By feeding on mussels, it prevents them from monopolizing the rocky substrate. Mussels are competitive dominators. Left unchecked, they form dense monocultures that exclude other species. Where ochre stars are present, their predation opens space for barnacles, algae, sponges, and countless invertebrates, creating mosaics of biodiversity. Remove the stars and diversity plummets, replaced by a uniform sheet of mussels. The experiments that revealed this effect in the 1960s helped establish the very concept of keystone species in ecology. The understanding that some organisms wield influence disproportionately large relative to their abundance. The ochre star is not merely a consumer, but an architect of communities, a predator whose absence transforms landscapes. But even keystone architects are vulnerable. Beginning in 2013, vast stretches of North America's Pacific coast saw populations of sea stars collapse in what came to be known as sea star wasting disease. Animals developed lesions, arms twisted or dropped off, and bodies disintegrated into white mush within days. Entire populations of ochre stars, sunflower stars, and other species vanished almost overnight. The cause has remained elusive. Viral pathogens were implicated, but environmental factors such as warming waters and pollution likely amplified the outbreak. The collapse reverberated through ecosystems. With sunflower stars gone, sea urchin populations exploded, grazing kelp forests into barren seascapes. With ochre stars diminished, mussels spread unchecked across intertidal rocks. The disease revealed not only the fragility of starfish populations, but the extent to which their predation held ecosystems in balance. The sledgehammer had been removed, and the locks of the system gave way. In the tropics, a different starfish has emerged as a force of destruction. The crown-of-thorns starfish, bristling with venomous spines and armed with up to 20 arms, feeds on coral by everting its stomach across living tissue and digesting it in place. A single adult can consume several square meters of coral each year. Normally, their numbers remain low, absorbed into the balance of reef life. But under certain conditions, populations erupt into outbreaks numbering in the millions. Waves of crown-of-thorns sweep across reefs, leaving behind skeletal rubble. Scientists have traced these outbreaks to nutrient runoff from agriculture and coastal development. Fertilizer-rich waters fuel plankton blooms, providing abundant food for the larvae of crown-of-thorns. With larval survival boosted, populations skyrocket, overwhelming natural controls. Human alteration of watersheds, in other words, has armed the reef with an army of sledgehammers. Management of these outbreaks is a daunting task. Divers inject starfish individually with vinegar or bile salts to kill them, but the scale of infestations often exceeds human capacity. Attempts at large-scale culling have proven costly and only partially effective. More promising are upstream solutions, reducing nutrient runoff, protecting natural predators such as giant tritons, and maintaining reef resilience to absorb impacts. Yet the tension remains. The same organism that, in some ecosystems, preserves diversity by suppressing dominators, in others becomes a scourge that devastates foundational species. The starfish embodies a duality, both regulator and wrecking ball, builder of mosaics and eraser of worlds. To witness their action in time-lapse is to grasp this duality. Tube feet march with mechanical rhythm, stomachs unfurl in slow violence, and prey is reduced to slurry before our eyes. Yet the long arc of their influence stretches beyond individual meals. They are the accountants of reef and shoreline, tallying growth and decline by opening space here, collapsing it there. Their power lies not in speed but in persistence, not in charisma but in inevitability. The mussel beds, kelp forests and coral reefs they touch all bear the imprint of their digestion. The takeaway is stark. Sea stars quietly regulate or wreck entire shorelines, depending on balance. Their biology reveals innovations: external digestion, decentralized hydraulics, regenerative resilience that defy our vertebrate intuitions. Their ecological role demonstrates how predators can shape entire communities, their absence as telling as their presence. But their fragility to disease and their capacity for outbreak remind us that balance is never static. In the tide pools and coral gardens, the slow march of tube feet is not just locomotion, but the soundless ticking of an ecological clock, one that can build or break with equal certainty.